Hello everyone, welcome back to my YouTube channel. Today I'm going to start another interesting series. In this series I will discuss text user interface in Fluent. You might know about it, but we will start from very basic to the advanced level of text user interface. Before jumping into text user interface, just I want to show you a quick example to show you what it can be done. Suppose we have this simulation and the fluid is entering from here and there is some convection happening on this wall. I want to run this same simulation but with different settings. For example, here at the inlet, I have 4 gram per second and temperature is 313 Kelvin and the total number of iteration is 20. So I want to run it, let's say with 5 gram per second and a temperature of 300 Kelvin, and I want to run total 50 iteration. I can do all these changes over here and I can run this simulation. And the other way is by using text user interface. So I have written those commands and I will quickly run those simulations. So let me copy paste over here. Here are those commands which will carry out all these changes. So once I have copy paste all these commands over here, I will hit enter and it will make all those changes and it will run this simulation. So you can see now we will go back and check. So see, the temperature is 300 Kelvin and the flow rate is 5 gram per second and the total number of iteration is 50. So instead of going one by one, I have just copy paste all these command over here, and with a single click it has made all those changes, initialize and then run the simulation. It means text user interface can save a lot of time if you can use it in your simulation. So in this series I'm going to cover these topics. So we will see what is text user interface, how to navigate between different commands, and a little introduction about text user interface. Then we will see how you can change boundary condition using text user interface. Then we will write journal file. Journal file is the file that you can read directly into Fluent to run this simulation. So I will tell you what is journal file. Then we will see how we can use text user interface to define material properties and to assign those materials to respective cell zone. To define one material is not a problem, but for example, if you are running a simulation of battery cells, let's say lithium ion battery, and you have a module of 20 battery cells or maybe 50 battery cell. I have run simulation where I had almost 90 battery cells. So you had to define separate material for each battery cell. So imagine you are defining manually 90 materials. There you cannot do all this manual work. You need to have this text user interface, and then each material need to be defined to each battery cell. So it will take a lot of time, maybe hours, to do all this work. But with this text user interface you can achieve this within a minute or within a couple of minutes. Then we will see how you can write a report definition using TUI. It is called TUI or text user interface. Then we will do some post processing with the text user interface, and at the end we will run a complete simulation with the text user by using text user interface. So of course I will not cover all these topic in single video, but it will be a series of video, maybe 4, 5 or 6 video, I don't know. But let's start with the introduction of text user interface. Okay, before that, journal file. Actually, journal file is simply a text file which contain all those commands which you can read directly into Fluent. So here and it has the extension of .gou. So for example, I had copy paste that commands over here, but you can read from here. Go to the read and read journal file, and can see here is a journal file .gou extension. So you can read directly from here, or so you can see it is reading from there, or you can copy paste. So it is same. So either you can copy paste or read through directly a text file. So those commands are written in a text file, and that text file is called journal file. So What is text user interface? So in Fluent, you have these two windows. One is this graphical window, other one is console. Actually, this console is a way to interact with the Fluent through commands. So everything what you do through this graphical user interface, you can achieve all these functionality using this console or text user interface. Whenever you come into the console, you just see this sign. So let's call it a greater than sign or whatever you can call it. So how you start? So when you don't see anything, just hit enter. So whenever you hit enter, you will see all these options. It works like window explorer, which contain folder, and each folder contain different folder, and it goes on. So I have hit enter, and you can see I can write all these commands. When you see this forward slash after a command, so it means it is like a directory. It means it contains further file. So let's go inside one of them. Let's go into the define. Yeah, here. So I will write define. So now you are in the define folder. Now you don't know what is inside the define, just hit enter. So it will show all those options inside the define. Now here, for example, here these two things. So if you write boundary condition, it means you will enter into another folder. Or if you hit or if you write, for example, units, so it means it is the action command or it is the last command, so it will do some action. So whenever there is a forward slash, it means it contains further option or further subdirectories. Or if there is no forward slash, it means that is the last action command or it will do some action. So let's write units. So now, for example, it is defining units for velocity. So whatever millimeter per second. It doesn't recognize millimeter per second. Okay. Centimeter per second. Yes. No. Sorry. It didn't recognize because we are not in the velocity, but we are back in the define. So, but anyway, we will come back later just to see how it works. So now you are in the define folder. So if you want to go one level up, just write Q. So Q from quit and hit enter. So you will go up. And again, you will hit enter and you will see all these options. So that's how you navigate into the different options. And it has the subdirectories for, so a few of them you can recognize solver. So it contain all those options related to solver. Then report, it is related to report definition, mesh, file, plot, and we will see a lot of them one by one as we will progress. Second thing, here you don't make spelling mistake. It means it is smart enough to recognize what you are writing. For example, it is mesh. So if I write MES and hit enter, it will recognize as mesh. So you don't need to write the entire word. If you write initial three words, so it will recognize. If if it will have two or more command which will have same three letters, so I think there are some rule you can check into the help, but I think there are some basic rule that you can check, but it can recognize the short word or short form of many commands. So if I hit Q, so I will go up. Similarly, let's go into the I don't know, define. If I go into the define, so you can see and then hit enter. We were here before, so you can see here we can define boundary condition, custom field function, dynamic mesh, injection, material, mesh interface. So we can do a lot of things over here. Today we will see how we can save file through this text user interface and how we can read the files. So for example, I have this simulation and I want to run this case and data file. For that, for that I need to go into the file because I know that, but you can recognize with the name. Okay, also exit. If you write exit, so it will exit through from Fluent. Okay, I said I want to save this my case and data file. So for that, I will write file and I am in the file folder. I don't know what option do I need to use. So for that, what I will do, simply I will hit enter. Now here you can see a lot of options. So here you have read options, here you have set option, and here you can see write option. I can write only case file, so it will not contain data or the results, or I can save case and data file. So I want to save case and data file, so I will say write minus case minus data space. Okay, I'm writing this case and data file, and then I have to hit space. I have to provide the name. Let's call it introduction.case. You can see it has written that file introduction.case, and here you can see where did it save. So it has saved into the your main folder or main directory where you are running your simulation, introduction.case.data.h5. So that's the extension. Similarly, you can go outside file, and here you can read same case file. Okay, let me open a new Fluent, and we will read this exactly same file. So let me open a new standalone Fluent. Here you can see there is no case or data file, and we want to read that file that I had written before with the name of introduction. To read, we already know we have to go into the file. So I will write here file, and now I'm in the file folder, and here I need to use read case and data. I can use this one, case and data, if I want to read result as well, or if I want to read only case file without result, so I will use this read case. So I will say read minus case, and what was the name of case file? Introduction.case. I have made a mistake. There is an extra e. With arrow key, up and down arrow key, you can you can just go to your previous command, so it works like any other programming language. I have written read case introduction.case file, and you can see it has read that case file. And let me display. If I go to the cell zone and I display over here, and you can see the case file is over here. Previously, I have shown you this example where I have written these commands, and I have run this simulation by using these commands. We will do this exercise, and we will change these boundary condition by using these commands, and we will run this simulation. Let's start with the boundary condition. Whenever you want to define something, you always start with the define. Simply write define. Now you are in the define folder. We don't know what option it contains, so we know the drill, just hit enter. Now you have all these options available into the define. We already know we want to change the boundary condition, so here you can see the boundary condition is over here. So we can write boundary. We don't need to write complete command. We can write some initial letters, boundary condition, and hit enter. Now we're in the boundary condition. Again, we'll hit enter to see the available commands. So now all these commands are available. Do we want to change pressure outlet? Do we want to set something? Do we want to change something on wall? We know that we want to do something with inlet, and this one is mass flow inlet, so it means we need to find out mass flow inlet. And here you will see somewhere is mass flow inlet. I will write mass flow inlet. Mass flow inlet, now it is giving you this zone ID available inlet. So I had said I want to change boundary condition. Which boundary condition of mass flow inlet? Because there is only one mass flow inlet, and it has name of inlet, so that you can see over here. If there would be more than one inlet, could be inlet 1, inlet 2, inlet 3, that you could see over here. So you would have seen here inlet 1, inlet 2, inlet 3. So now we wanted to change this boundary condition. By chance it has the same name as the boundary condition inlet, so I have written inlet, and I will hit enter. I want to change the boundary condition of inlet. Now reference frame absolute, yes. Whatever you see in square bracket, so that is the default value. To take the default value, you can simply hit enter or you can write yes. I don't want to change, I want to keep it as it is, so I will hit enter or I will write yes. So we can do in both ways. Let me hit enter and it has taken it has taken default value of yes. Mass flow specification method, mass flow rate. So again, I can hit enter to take the default value or I can write yes to take the default value. If I want to change this one, I can write no. I will write here yes or I will hit enter. Previously I had hit enter, so now let me write yes just to try different option. Now use profile for mass flow rate. So I don't want to use profile, I want to use a constant value. We will come for profile for maybe some complexer problem. So here now default value is no. It means I don't want to use profile, but rather I want to use a constant value. So let me write no, or I could hit enter. And then mass flow rate, constant or expression, whatever we had defined over here in the previous step. Now we need to define its value. Now I want to use it 5 and then I will hit enter. Use profile for total temperature, no, so I will hit enter. Then I'm not using profile, so it means I will be using a constant value. So previous value is 313.15. Now I want to use 300 Kelvin. So I will hit enter. Here you can also see the units in bracket. So I will hit enter. Use profile for supersonic initial gauge pressure. No, I don't want to change any other property. So it means I will take the default value. It is same over here. So for example, here you see all those options. Here you don't set all those options. You just take default value. So when you say apply, it means you accept all those default value. The same thing we are doing over here, but it goes all those values one by one. For all those default value, we will hit enter. Again, gauge pressure. So the gauge pressure or the outlet pressure is 0 and I will hit enter. Direction specification. So we don't want to specify the direction, where I will hit enter or I will write no, both are same. Normal to boundary, yes. And then turbulent specification method K and omega. So here when I go back, so it has used intensity and viscosity ratio. When you go down, you see here are different options what you want to use. So default is this one, intensity and viscosity ratio. So you will see all these options one by one. So I will say no. Then it's a turbulence specification method, no. Intensity and viscosity ratio, that we had already seen, intensity and viscosity ratio. That's how we are defining, yes. Then we need to define the turbulent intensity in percentage 5. So we can accept 5 or we can change. So let's accept this one. Then turbulent viscosity ratio. So the default value was 10, so we are taking 10. If you want to change, so you can write number whatever. Let's write 8. Yes as well, I think. No, it won't accept yes. Either you give a numerical number or you will hit enter. So you have defined all those boundary condition, or you have defined all those parameters. Now we can check. So it is 5 and the temperature is 300 Kelvin. And we did not change 5 and 10, and you can see these are 5 and 10. Okay, that's perfect. So we have changed our boundary condition. Now we want to initialize and run this simulation. So for initialization, we have to go 1 or 2 level up. So for that, I will write Q and hit enter. 1 level up, again Q and 1 level up. You can recognize that for initialization, I need to go in solve. When I will hit enter, there you can see there will be a folder for solve. So yes, I will write solve and then I will hit enter. I see two different options in the solve. we want to initialize. So here you can see initialize. I can write INIT. You can see it has recognized initialize. And then here we have different option for initialization. So same here, if you go into the initialization, so you have standard initial, hybrid initialization, standard initialization, from which cell zone, so all these options over here, and you can set default values. You can set for hybrid initialization values, so you can set all these values. So we can do this hybrid initialization. I have just copy and paste hybrid initialization. Current data has not been saved. Okay, do you want to discard the data and proceed with initialization? Yes, we want to proceed with initialization, and we have initialized our solution. Now initialize has been done, so we will go back one above to solve our solution. Now we want to iterate our solution. So I will say iterate. I have written a complete word and it doesn't match with any of this thing. So I will write ITER, then hit enter. And it is asking how many iterations do you want to run. Let's say 50 and hit enter. Your solution has been finished. So we can check results. So without discussing results, just to see that our solution has finished, let me draw temperature, and you can see the temperature, because here the temperature is 300 Kelvin and I have applied some convective boundary condition that you can see over here. So that's why you can see the temperature is changing. But anyway, the discussion of the result is not the scope of this video. Just I wanted to show you how you can change boundary condition and how you can run this simulation. So now next question. I have written all these commands one by one, and when I have written all these commands one by one and I have run all these simulation, so what you can do, you can write all these commands, what you can see in blue, you can write all these commands in a single line and you can run. That's what this text file over here that I had shown you before. Let me pull that text file. So here are all those commands which I have written with you on this console. So you can write all these commands in a text file like this, and then you can copy paste at once, and then it will run all these things at once. It is a little bit complex, or it is a little bit overwhelming, as you cannot see when you write in a single line, you cannot see what these commands represent, but when you are writing this file you would know what each command mean. But anyway, we know this 4 is the value of the mass flow rate that we can change. Let's make it 3, and here is the temperature that we can change. Let's make it to 90. Here this one is the 5, that the intensity in percentage we can make it 3, and here is 10, we can make it 8. So when I have written all these things in a single line and I will hit enter, it has changed all these things within no time. And when you go over here, you can see this one is the 3 gram and 290 Kelvin, and 3 turbulent density is 3 and turbulent viscosity ratio is 8. Now the question is, either you can write all these commands over here in a text file like that what you have written over here. So you will write over here and you can put in sequence. So these should be in sequence, because when you write this one, the Fluent go in sequence exact in the same order what we have gone through over here. So it means if you change the order, so you might change some values. So that's a drawback, you can say, or that's a thing where you have to be careful with. So if you make a small change, so it can change your command. And how we can write this, there is a better way for writing this journal file from scratch that we will discuss in next video. But before that, there is another thing. the general file what you have created in one version, so when you are using for different version you have to be careful. Every version the sequence of these commands could change. So it means if you have written a general file for 2023 R1 that for using for any other version you need to check the sequence. So if you will use add, there are very high chances that you will make mistake or the sequence will be different. I have seen this quite often because I have worked with 2019, 2020, 2021, 22, 23, and I am using these files, and for every new version I always make changes. We have seen the introduction, we have changed our boundary condition using TUI, and then okay, next I will show you how we can write a general file from scratch. To write general file I have chosen this example. So we have two pipes. I have called this one is the main pipe, and this one is the branch pipe. We want to simulate that the fluid is entering at a velocity of 0.3 meter per second at a 60-degree, and from branch at 0.5 meter per second at a 20 degrees Celsius. And we want to see the mixing of these two streams. We will write a general file so that we can change boundary condition, these two boundary condition, by using general file, and we can also simulate with the same general file. So let's get started. Here I have imported the geometry and it has already been meshed. For this particular example I have used Fluent meshing, and for that I have made a separate video, and I will also provide the link for that video for Fluent meshing. As I mentioned in my previous video, you can define the boundary condition on this console, but you have to write every command one by one. So we want to avoid that. For that, what you would do, you will go to the file, and here you will find one option, it's write, and here write general file, write start general, and here you can select your location. So I'm selecting this location, and let me call my first journal file. I have just given a name and click OK. So before starting, one thing, as I have gone over here and I have said okay, I want to write a journal file. So once you set start journal file, now here is a stop journal file because it has already started. When you start a journal file, every command, doesn't matter if it is from console or from graphical user interface, every action will be recorded in that journal file. We will see how it looks like. So it means we will write all those commands over here that will be recorded, and then we can use that one. Of course, for every new journal file, you have to go through that process one time. But once it has been recorded, you can modify and use it again and again. So let's come over here, and in previous video you have already seen how we use this one to define boundary condition. So I will go this one quickly. So to define boundary condition, we always go first in define, then I hit enter, and then to see the different option, then we have to go into the boundary condition. You can see over here, just to show you, with hit enter you can check what available option are there. Anyway, then boundary condition, then we have to go velocity inlet. I know because I did that before and I use a lot of time, so I know. Then velocity inlet, then you have to provide the velocity name. Let me use inlet minus main. I want to change this inlet minus main. Enter. Velocity specification method, magnitude and direction, no. Component method, no. Normal to boundary, yes. Absolute frame of reference, yes. Use profile for velocity magnitude, no. Use magnitude constant, yes. It's 0.3, so yes, let's say 0.3. Then profile for pressure gauge pressure, no, we don't want to use profile. 0 Pascal, yes. You can write 0 or hit enter, yes. Use profile for temperature, no. For main, the temperature was 20 degrees C, yes, but we can enter a number or you can hit enter. Yes. Turbulence specification method K and omega, no. Intensity and length scale, yes, we want to use this method. How much intensity we have in our case, let's say 10. You have to use your number, but I'm just using this number. And the length of the turbulence scale is 5 millimeter. It depends on the size of geometry. In our case, it will be approximately 5 millimeter. And we have defined our boundary condition. So now let's stop our journal file and stop journal file. And you can see over here, journal file is closed. Now let me open journal file and see what we got over there. Here is our journal file that we got after recording our journal file. So this first line, it record on which version we have written this one. So we will leave this one as it is. The second one we can delete. So, and to define other one, so this one we had defined all these command we had written one by one. So this one is written for this one, inlet main. So we can copy paste this one, and instead of inlet main we can write our name for the second inlet, that was inlet underscore branch. And here you can see, so all these options we have used, so all these will remain as it is, but here 0.3 was the velocity, if you remember. So here we want to change it to 0.5, and this 20 was the temperature, and we will change it to here 60 degree. So these we have defined for our second boundary condition. So similarly you can record for the solve, but for that I have already done that, and here are for solve command. So let me write over here. So to initialize, solve, initialize, hybrid initialization. So you can use hybrid initialization, standard initialization, whatever you want to use. So you can write over here. And yes, it is used to say if you want to override, yes. Then the second one is to iterate your solution. So now we have got our journal file. So now if we read this journal file, or if we copy paste all these commands, it will use all these commands to make changes and run simulation. So let's try in both ways. I have copied this one. If we go to over here, let me go outside, and so you can see I have paste over here, and then I will hit enter, and you can see it has run. So applied, okay, let it run. So here I did copy paste. So here it doesn't show what happened, but for this one is the output for the inlet main, and this one is the for inlet branch. It was showing for both option, inlet main and branch. It is not showing what we have selected, but we have selected inlet main, and here we have selected inlet branch. Then this line correspond to the hybrid initialization, because we know that's how hybrid initialization look like, and here you can also see hybrid initialization is done. And then after that, this one is for solving your simulation. So we can check our parameter, for example 0.3 and 20, those one for the main one. Here boundary condition, inlet and main, sorry, the first one is the branch 0.5. Yes, here you can see 0.5, 60 degree, go to the thermal, and it is 60 degree. And for the second one 0.3 and 20 degree, yes, that's correct. And so just to be sure, let's change these two again. Let me make it 2, and instead of 20 let's call it 10, and here instead of 5 let's call it 6, instead of 60, and let's do it 80, and Control S. I have saved this one. Before that I did copy paste. Now we will do another way. So we go to the file, read, and then journal file. And here if you go my first journal file, so it contains our all those commands. Click OK. Says, does the journal file contain command that read or write files after the calculation begin? Yes. Okay, yes, and so it is reading and it is running those simulation. After 10 iteration, we can check if those changes have been implemented. So what we did zero point 0.2 and 10, 0.6 and 80. Let's check again. Yes, 80. So in branch 80 and 0.6, that's what we did. And similarly 0.2 and 0.10. Yes, perfect. So now you can see how fast you can run your simulation. So now if you want to run a different simulation by changing these parameters, so you can do it really fast by just by changing all those parameters in your journal file, and you can run your simulation very quick. So it will save a lot of time. Imagine if you have really long setup, so you can just make your changes over here and then you can run your simulation. That's how you can write your journal file, and you can use it for your simulation through this console by copy paste or through by reading from here file. At start I had said another thing, it also record whatever you do at your graphical window. So let's check this one as well. So for that I'm going to write another journal file, new journal file. Let's give it a name, graphical user interface, I'm just saying. Okay, and okay. Now let's do over here. Let's go to the inlet and go to the branch. Change the velocity for 0.6 to 0.5. Apply OK and close. And now let's say we have did, and now I'm going to stop our journal file, and then we will check what is in that journal file. So here is our journal file for graphical user interface. You can see for graphical user interface it is quite complicated. Maybe you can recognize, for example, here velocity inlet, and here is our value, and so it record everything what we did. So it is, for example, navigate pane frame 2, so it is recording where we are navigating and what we are selecting. It will get quite complicated. You can record all of your action from GUI, but that's not quite practical. Imagine if you have you are doing a lot of things. For example, you are changing velocity, temperature, you have a couple of boundary condition, and you are writing report definition. For each task for TUI you have only one line, but this one line correspond to all these line in GUI, so it can become really messy and prone to a lot of errors. That's why it's not a good idea to use journal file for graphical user interface. In previous videos I have discussed first 3 points. Today we will see how we can write a journal file to define a material and then assign it to a particular cell zone. So let's continue. Before that, let me show you our final goal of journal file. Here is a sample of a journal file that I have written for one of my work. Here I have written what this file can do. It is just for the information. The comment in the journal file is written with these semicolon. For example, here I am defining a material. So here are different cell zones. I was assigning the material aluminum to these cell zones. Then I wanted to delete these material. So here is the command how we can delete this one. Then here I am writing the orthotropic thermal conductivity of the battery cells. Here we can see I have a lot of battery cells, and each battery cell was having different thermal conductivity. We can do all this stuff manually, but it will take hours. And with this scheme command, it can be done within a minute. So we want to achieve something similar at the end of this course. So let's start with our next goal of defining the material and assigning it to a cell zone. As I have mentioned earlier, to record all of our command, we always go to File, then we go to Write, and we say Start Journal File. And then we can write the name of the journal file, material. We want to define the water, so we will start from define and then we will go to material. Then we want to change create, so we will say change create material name. So here's something tricky, material name. So you have to give the material which is already present. So it means here we are saying we want to change or create material. Change mean here what is already here that you can change. We want to change air, and now you have to assign a new name. New name, let's call it water. Now he is asking if you want to change the density. We will say yes. And here are different methods to change the density. We can use constant, and there are a lot of options, but for the time being density we want to go let's with polynomial. So before going here, let me show you how does this work. The polynomial is defined in this way. You need to define the coefficient of your polynomial. It always goes like that: ax node bx plus cx. First you have to give the coefficient of x node, then x1, then x2, and so on. So it depends how big your polynomial is, but it will always start from x node. So going back, we want to define as a polynomial. You can say constant, we will see it in a minute. Okay, polynomial. Now number of coefficient. So here you have to define how many coefficient you have: 1, 2, 3. So if it is constant, that will be 1. 2 mean a node, ax node plus bx. So we will have 3 coefficient. I will write 3. Then first coefficient here. First coefficient is this one. First coefficient, then second one, second, and then the third ones, and third, and I will write third here. Now change CP. Do you want to change the heat capacity? Let me say yes, because for water and air it would be different. Again, you have different option to define the method. So you can constant, piecewise, linear, piecewise, polynomial. So it's up to you what kind of heat capacity you have. Let's go with the constant. For water it is somewhere 3800 joule per kg per Kelvin. Then change the thermal conductivity. Yes. And again the method is constant, and the value is 0.6. Then change viscosity. Yes. Again here are different method, but I am going with the constant. And viscosity, I'm just giving some values. They are not actual value, but you can use whatever you like. Then change molecular weight. Yes, molecular weight, normally if you go through graphical user interface you don't need to define, but here at the text user interface it always asks for everything. Molecular weight you don't need to give because it will not be used anywhere, but if you know, so you can give the correct value. So for air it is different, so change molecular weight, yes. And the value for water is 18. 28 was for air. Change thermal expansion coefficient, no. Change speed of sound, no. Now here, change create mixture and override air. So do you want to override? If you will say no, so it will create air plus water. If you will say yes, so it will override air and you will get only water. It's up to you. Do you want to override or not? So I will say no. And then we got here water. So just to check, we can go inside and we can check. So here is polynomial we have given. If you go in here and you can see polynomial 3 coefficient 1, 2, 3, and here is the curve. And similarly all these values we have changed. Now our next goal is to assign this water to this cell zone. We will start from scratch. Again, define, and you assign material, because I said the assigned material is air and we want to assign water, and you assign material in boundary condition. boundary condition, and then so here all these things what you can change, and here you can see fluid. So it is little bit confusing. This fluid is not the name of this fluid, but it is the type of cell zone. So either you will get here fluid or solid, because we will get only two type of cell zone, fluid or solid. Fortunately or unfortunately, this cell zone and the name of a cell zone is same, but remember this one is the type of cell zone, not the name. We want to change because we don't have any solid cell zone, so that's why we are not getting any solid. We want to assign the water to this cell zone of the fluid, so we will write fluid. So here is the type of cell zone. Now here is the name of that cell zone. So here you could have whatever name, zone 1, zone 2, or you could have multiple names. So if you would have 3 or 4 zone, so you would get all those names over here. So here you will write the name of the cell zone for which you want to assign the material. So we have only one cell zone, and that its name is fluid. So we will write fluid. And it is asking material name here. So this cell zone fluid is having material of air. So change current value. Do you want to change its material air? So it has air, you want to change? Yes. What do you want to assign? So we have water. And we will assign water. And then we want to assign source term. You can write no. Fixed value specify. So again, no. Frame motion, no. Then, or you can just simply hit enter. Other than that, we don't need to change anything. Mesh motion, no. Enter yes or no, continue. So let's enter yes. Laminar zone, these are type of properties. We will see what are these properties. Laminar zone, no. Porous zone, no. 3D fan zone, no. And that's it. Let's stop over here. Stop general file. Okay, let's see a few of those properties. So for example, if you go in fluid, and here you can see if you want to activate any of these options, frame motion, 3D fan, source term, mesh motion, laminar zone, fixed value, porous zone. So we set all these to no. That's why we have hit enter or we press no. And here you can see the value of the water have been assigned. Now let's go back and check our file. Okay, here you can see a lot of things because in between I had used the graphical user interface, that's why it has recorded everything. So you can delete all those things. Only these two lines are of interest. This line you can see it is changing the air to water, and it is defining polynomial, 3 polynomial, and these are coefficient. Then all those values are constant. And here it is assigning to this fluid we had before air, and it is assigning water. So here it has asked, do you want to change? We said yes. Now we are assigning it water, and that's how you can define your, or you can write a command for your material properties. Coming back, in last video we had defined our boundary condition, and we had run our simulation. Now we had defined our material, and we have assigned this material to that fluid zone. If you want to test, for example, let's change it over here. Here we can copy this one, for example, and if we go back, you can see here is water, and if I copy paste over here, and it will change from water to air back, and it has come back to air. And if you want to go back, so you can go here and you can write it water. Now for example, you want to run your simulation, and here you want to change your velocity. Velocity should be 5, and here this velocity should be 4, and your material property, this one is the thermal conductivity, it is not 0.6, 0.4, and your viscosity is not 0.002 but 0.01. You have made all those changes. You can copy all those commands and you can paste over here, and hit enter. So it has made all those changes and running simulation, and your simulation has finished. Here some red thing. Here are some errors, so we can check this error. The error is because we already had water. If you go over here, we tried to define water, but we already had water over here. That's why we got this error. So that is also one thing you should be careful. If your name is already existing, you will get error and you won't be able to define properly everything after that. It means first we have to delete this one. Let's go back here, make it air. Let's delete this one, and now let's copy paste and run. You can see it has defined water over here, and if you will go, just give me a second. If you go inside, so it did not change because here was air. But anyway, you know what to do. So you can change your parameter over here, and you can copy paste, and you can run your simulation at once instead of going all those 3 steps one by one. Let's also check the boundary condition, which we have changed through journal file. Go to the boundary condition, inlet boundary condition. It is 0.4. So let me pull this boundary condition. We had changed to 0.4 to inlet branch and 0.5 to inlet main, and we can see inlet branch is 0.4. That's correct. That have been changed, and inlet main 0.5. We had also changed the viscosity of the water, that we can check. It is 0.4 and viscosity 0.1 and thermal conductivity 0.4, that we had changed over here, 0.4 and 0.001. So everything is working fine. Next we will discuss the loop. Here you can see I have 46 number of cells or number of cell zone, and for that either I have to write all this command 46 time, or I can use loop. So here you can see I am using do loop. We will see how to use this do loop to do some repetitive work. For example, if you want to define multiple report, you can use from report. A point came to my mind, so maybe as an assignment or as your practice, you can write a command to define your report. So here, for example, I have defined outlet temperature. Maybe you can define report for the pressure at the inlet or outlet, whatever you like. Just try to write a journal file for a report definition as a practice. Before using loop or if statement, you should have a basic understanding of scheme language. I will give you a really brief introduction of scheme language so that you can understand the loop or this if statement. In Fluent, scheme language is used to write the text user interface. It is little bit different from the conventional languages. So in conventional languages, you write variable, then operator, then second variable, and it continues like that. But in scheme language, you will see a lot of parentheses. So first of all, every operation is performed within a parentheses. In parentheses, you always write first operator, then your variable, or it's called operand. For example, I want to add 5 and 2. So I will write first plus, then 5, and then 2. It will do this addition operation on 5 and 2, and you will get an answer of 7. And you have to write this in parentheses. If it will not be in parentheses, you will get an error. And in the second example, your operator, for example, is minus, and your variable 5 and 2. So it will subtract 2 from 5. This negative sign is not the sign of 5. This one is the operation, and 5 has a positive sign. So 5, this operator, then 2. So you will get an answer of 3. When you want to have a minus 5, so you have to put minus with this 5. So now it will subtract 2 from negative 5. So then you will get negative 7. So that's how this scheme language works. So now let's have a look on our loop. Here I have already written a loop to define 3 report definition. I am taking the same example as before. We have two streams. One is entering from here, one is from here, and a mixer is leaving from here. So let's see, we want to define 3 reports. One at this inlet, one at this inlet, and one at this outlet. And for that, want to define 3 report. For that, I have written this loop. First, let's run this loop, and then I will talk about each and every line on this loop. Let's go on Fluent and see how it works. Here in the report definition, you can see I have only one report definition for outlet temperature. I have copied all that text and let me paste over here. When I hit enter, and you can see it had defined 3 report definition: inlet 1, inlet 2, and outlet 3. Let's check what is inside in these report definition. So inlet 1 is the area weighted average pressure at the inlet underscore branch. That's good. Inlet 2 is the area weighted average pressure at inlet main. And similarly, if you see, outlet 3 is the pressure at the outlet. So you can see with this script we have defined all these 3 report definition within 2 or 3 seconds. If you had to define manually, so you would go over here, then go surface report, and then you would go area weighted average, you will write name, and then you will select. That you have to do manually for each and every report. Suppose if you had here 20 report, it will take maybe 15-20 minutes or half an hour, and with this script it will hardly take 10 or 15 seconds, even less than that. Let's see what this report says. We can talk about here or come over here. First line define is the internal function, and it is defining, I am defining a variable. As I said, first you have to write this operator. I wanted to define 3 number of reports. I have given it a name or given it a value of 3. Then I have a define report name. I wanted to define my report name. Here I have written empty inverted commas because I want to define name in the script. When you want to define a list, you do like that. Here is the define report name. Report name is a name of a list, and this list will contain the name of all the reports. Then I am defining another list, cell zone list. So whenever you want to define a report, you should know all of your cell zone. So I am defining a list containing all these cell zones. So my cell zones are inlet branch, inlet main, and outlet. You can get all your cell zone name from here or whatever. Sorry, these are not cell zone, but these are surfaces because I want to define this surface report. Coming back again, you can see first it will check this one. Operation will start from here. It will come over here, it will see define. Okay, then it will look for some variable or whatever you want to do. So I am giving it a name, cell zone, and this apostrophe, it is used to define a list. So I am defining a list containing all the name of my all 3 surfaces. Then I want to loop over all these 3 surfaces to define my report. So it always start with do. So I am saying I want to do a loop, and here I am defining a loop iteration. Here C is the variable name, it could be anything, nxc, so it will be just the loop counter. It's a variable that's a loop counter, and it will start from here. So I have defined a loop, so that will start from C and its value is 1. So then in the next parenthesis, what will happen? And there will be an increment plus in the C by 1. So first loop will start with 1, then it will come back, it will add 1 in the C, then it will be 2, and it will continue. So up till when it will continue, then it says greater than C, when C will be greater than number of reports. Have how many number of reports? 3. C will be 1, 2, 3, then it will come back over here, it will check C will be 4 and number of reports 3. Now C is greater than number of reports, so it will stop. So it means this loop will continue for 3 iteration. If I will write over here 10, so it will continue for 10 iteration. I think this line is clear. Now I just added this one. You don't need to add this one. Instead of adding this if loop, you could do other way around. So we will check how you could do. So but what I am doing here, I am just want to define my report names. I'm saying if C is less than 3. When C is less than 3, you don't need to write over here. When C is less than 3, it will use this operation. Otherwise, it will continue with this operation. It is starting a statement or starting a loop set. So set is just to define something or setting a name or anything. So you want to set something. So here I had defined this set and report name. So I am setting the name in the list in my report, which I have defined over here, report name. And string append. String append, what is this doing? It is appending a stream to what? So I have said here is my string, and then number to string C. It is converting number to string. And which number? C. C, we have a number which is coming over here, and this operation, so it will start from here. What this bracket will do, it will convert C into a string. So see, we had a number, and this operation is converting number into strings. Here we will get a 1 as a string. Then this bracket will finish this one and this one. Let me write over here, then we will left with this bracket. Just let me make it over here, and it will convert into 1, and 1 will be a string. As I said, this one will convert C into a string of 1. And then the second operation will start, string append. It will append these two strings, so it will become inlet underscore 1. So now you get this string. So here it is setting, so your report name, it is becoming this inlet 1. Now your report had one entry for C is equal to 1. Then it will not calculate this one because it will be calculated once the C will be greater than 2. Then here we have a defined zone name. So here we had defined the list, but from this list we want to pick one entry in each loop. So we do this one through this line, list reference. So we are referencing a list. Which list? Cell zone list. So we are referencing this list, and this one is defining the location. Plus C minus 1. In first loop, C is 1 and minus 1 is 0. Indices will start from 0, 1 and 2. When in first loop, list reference will pick a value from cell zone list which will be at 0 index. That's how we are defining our zone name. So it means in first loop we have defined our inlet, which will be inlet 1, and we are picking first entry from this one, which will be inlet branch. And then here comes our command. So I am not going into the detail of this command because this command you can write by yourself by following my previous video. It is similar as we did before. But here are few things in this command. Here I have written this sign with A. This one is used as a placeholder. This one and this one. So it means I am not giving its value over here, but this value is given at the end after comma. After this inverted commas. So it means this one is the placeholder. It will execute this entire command, and it knows I have a placeholder one over here and one placeholder here. So first placeholder will take first variable, second placeholder will take second variable, and the first variable is the zone name, report name. Report name we have defined over here, that would be inlet 1. And the second placeholder, that is the zone name, and zone name we have defined over here, that will be at 0 index, and that will be our inlet branch. And then we have over here comma. Comma is used when when we are writing some command, so sometimes we hit enter or we accept the default condition. So this comma is used to accept the default condition. And this one, this entire thing, This one is used just to write this entire command in a single line as a string. This one is the just formatting. There is nothing special. It's just a way of writing this entire command. Formatting, and it is text interface menu load string. So it is loading this entire string. It means it will define all these one and it will come over here, solve, report definition, add. So this entire command will be executed. It needs report name. Oh, sorry, here is a placeholder. This placeholder equivalent to report name, and report name I have told you how it will come over here in this one. And similarly zone name that will come from here. And as I said before, you don't need to do this loop. For that you can do in the similar way. For that, for example, you don't need to do this one, and you don't need to do this entire thing. Yes, so you can define, let's say, another list, but that will be your report definition list. And let's say you want to give them the same name, or you can use whatever name. So let's keep same name. And then you have to pick one entry in each loop from this report definition list. So I'm just copy pasting this one. Define zone name, and here I will use here I have to give this name. Let's call them report name because I have used that variable. Report name because here this variable is this one. List reference, we are referencing this list, and I can reference this list, and that's it. We are good to go. So let's try this one. Before that I have to delete no, I don't need to delete because now I'm using different name. So remember, if you have the report definition with the same name, so you will get an error. And here I have used different name, so I don't need to delete. So let me copy all these, and I can paste over here and hit enter. And you can see it has defined these three: inlet branch, inlet main, and outlet. So that's how you can use loop or if statement in your text user interface. I hope it was clear and useful, and if you have any question or anything doesn't make sense, so you can always leave a comment below. I would be happy to help. Let's continue with our series of text user interface. I have discussed all these points. We are going to run a complete simulation, which will start from defining boundary condition, defining material, assigning material to respective zone. Then there will be a general file, or there will be a function using a loop statement, do loop, define report condition, and then at the end some commands will be there for post processing. Let's see what it looks like. Here is a general file that we have developed. So let's go through these one by one. If you have followed, you can understand, or you would know all these commands. First, define velocity boundary condition. You know that we had written these two commands to change the boundary condition of these two, inlet main and inlet branch, that we are using in our example. Then we had written this command to define a material. We are defining material, and in this material we are defining water as a water density as a polynomial. So here you can see polynomial with 3 coefficient, and these are 3 coefficient. Then after defining material, we have to assign this material to its respective cell zone. Let me write. And here is the command that we had used to assign this water to this cell zone. Then in my last video, we had gone through this do loop, and here we had if statement that I had removed, but you can see that if statement in my last video. So this portion of the video is defining 3 reports, which will be named as inlet branch, inlet main, and outlet. And we will be defining pressure on these 3 boundaries. And then this portion of the command, it will initialize our solution, and it will iterate for some iteration. We can change iteration, let's say 50 iteration, whatever you would like. And this last portion will create the velocity contour and pressure contour for velocity magnitude and total pressure. So I haven't gone through this command, but if you have followed my video, so you know that how we can write a general file for any function. So we did for velocity, we did for material, assigning material, this one. So you can do this by yourself and it would be your practice. So now let's run our simulation. So let's copy this one. And okay, before that, let's change some parameter. Mean it's up to you. So I'm saying, okay, this one is not 5, this one is 3, this one is 6. These are our velocity. Here we have temperature. This temperature is 60 degree. Here is the intensity. We are defining water. Let's say we give it another name, water liquid. And you can also change these names. I am okay, let's call them just actually, it doesn't matter. Keep as it is, and these are the names. So let's copy all these and go to our simulation. Before that, let me show you in the material we have only air. So it will create over here the water, and this water will be assigned to this fluid which is having air. We will check all these parameters. And then we are defining report. So here you can see there is no report definition. Here we don't have any contour, and you will see here velocity and pressure contour. I have told you in my very first video you can read file through here, a scheme. You can go there. Alternatively, you can just copy paste over here. So here are all these commands. So after copy pasting over here, you will just hit enter, and that's it. So let's wait, and then we will see what all these commands have done. This simulation is running quite fast and we will be done in a second. Okay, now let's check. So here you can see the water liquid have been created. It has a density of polynomial with 3 coefficients that we had over here. These are these 3 coefficients you can see. And you can also check the boundary condition. For example, inlet branch we had set 0.6. Here is inlet branch 0.6 and temperature of 60 degree, that we can verify temperature is 60 degree. And similarly inlet main 0.3, temperature of 25 degree, that's perfect. And if we go further, here we didn't have any report definition. Now we have outlet, inlet main and inlet branch. It has created 3 reports. Area weighted average pressure that you can see over here, we were creating surface report, and we were creating total pressure, that was surface area average, and that we did in last video in pretty much detail. You can check my previous video for the detail of this law. And the last but not least, here are 2 contour, pressure contour and velocity contour. So you can go and display which has created total pressure, that is here our total pressure, and similarly our velocity contour is here, and that's the velocity contour. So that's how you can use this journal file to automate your simulation, and it can save a lot of time. So you have written, for example, now I have written this file and I can change any of these parameter and I can run this simulation. Maybe a takeaway from here, for example, now I want to use this file once again. First 2 command will work. Now if I will go over here, if I will try to do this one, I will get an error. Let's try. So here it did not run because it says water liquid already exists. It means if you are defining some material, that name should not exist before. So that's why we are getting this error. So you have to delete this one in water liquid. You can delete from here, or alternatively you can add one command over here before. That I need to check how you will write or how you will do, but you can write a command for water. Okay, yes, that is also interesting. Let's try to delete this water before. Okay, define boundary condition, then we had change create, Sorry, define material. Sorry, one go define material and change create, and here you can also see delete. So let's see delete and water liquid. So ideally it should delete, but it will not delete. Let's try, and it cannot be deleted. Okay, because the material still is in use by fluid. So you can see the error is here. It is still in use. So if we go over here and check, it means it is still in use by this one. So it means to delete this one first, we have to unassign this one over here. And for example, let's try that you can delete. Yes, so yes was here, that has been deleted. But so to delete water liquid, you have to first remove from this fluid. That you can do from here as well, but for that you can write a command. Here is the command that we want to unassign this one. Let's go back here, fluid. Yes, instead of water it should be air. And so now we will, it has water liquid, and now we are assigning this one is air. And you can see now it has air, and now we can delete this one. So define material, then we had delete and then water liquid. Now it has gone. So what you can do to be on safe side, what I do, I always, before defining a material, whatever I am defining, so either you should take care of the name, or what I do normally, I just write this command always before. I always assign air to all the cell zone. So that's why I never delete air from my fluid. So what it will do, if this fluid is have water as a material, so it will assign air. If it already has air, so it will not make any difference. So now if you will run again, so it should run. Or let's say now you can run this one easily. Let's copy paste, and now if I say, and now so it has created water and air. So let me do it again. So I have copy paste these three commands. Oh, sorry. Now we want to delete water. So for that you can write your command. That was delete and water liquid. So now this one will assign this fluid by air, and then it will remove water, then it will create water. So now it will run every time. You don't need to bother about if water is already present or not, that material. So it will run always without any problem. So you can see it had removed. Let me remove this one. Anyway, that's how you can run your entire simulation. You can make changes in your this journal file, and you can run your simulation again and again, and you don't need to spend a lot of time on your manual work. That entire time could be saved. And that's it for today and for this entire course for text user interface. I hope you found this entire course helpful. If you have any problem or any question, you can write them in the comment below. I will try to reply as soon as possible. Thank you for watching, and see you in the next video.